Okay, guys. So we covered we talk about this Hadoop system, and I hope I understand. So for us, we do not need to become an expert of big data. Like we do not need to learn Java and also the programs like what showed in this video to operate the big data. But at least we should know the principles of big data processing. This is actually based on parallel computing. The logic is actually very simple. If it's too difficult to analyze a single chunk of data, let's cut them and let's allocate the task into different computers and each one will do their assigned work separately, and later on we have a higher level computer to aggregate the result. And so it doesn't matter what it's called, MapReduce or DAG. So the fundamental logic is the same, okay? And nowadays we also have other algorithms that can switch the rule of the computer. So for example, at one time, this computer is used as a slave worker, the one that received the smaller chunks of data and operate the data. If something's wrong with the master computer that is assigning the task, then we also have algorithm to switch the rule, like to promote the slave computer into some kind of a master computer. So that's actually all the development of big data analysis. It's a really a big research area, a big discipline. So we just need to know the fundamentals about that. And talking about that, if you recall, for the big data ecosystem, we also have two popular methods, the DAG and the graph model. So these actually based on the graph theory. This DAG is called a directed acyclic graph. So this one basically uses the lessons we learned from graph theory to find out, for example, what is the shortest path to search for information. And then what it does is to convert the original tabular data into graphs. So for example, in this tabular data, we could document the relationships between customer account. We have their ID, we have their property. For example, this ID3 is a student, this ID7 is a postdoc, and also we could have a table to describe their transaction. For example, 3 and 7, we define them as collaborator, and 5 and 3, we define them as the advisor, which means one customer account advisor, the other one. If you imagine this is as Amazon, so it could be this column could be the customer ID of a customer account on Amazon, and this one could be their identity and their property, and another table could show in the transactions like selling and purchase among all the customers. So instead of this DAG model or this graph model, they are pretty much similar. Instead of just using the raw tabular storage and analysis, they actually convert them into graph first. That makes sense, right? So let's imagine you have a big graph and each node or vertex is actually representing one account on Amazon. And the edge, which is the connection between the nodes, are considered as the transaction history. So then in that way, it's mathematically, we can convert the tabular information to this one. And when we have this graph, we can apply graph theory to see, okay, if I want to find the most popular seller on Amazon, how do we do it? Then there's a whole bunch of graph theory can give you the answer very quickly, like based on the connectivity or whatever. Or if I'm running this Facebook account, and each node is a Facebook account, and the edge represent their communication on Facebook. So if I want to say, what is the relationship between, let's say, Shuyash and Hari, then basically you have this graph, and we run this mathematical graph analysis. We can find the connectivity, like how many steps, the shortest steps to connect the two nodes together. So in that way, we can save the time to run a whole lot of sorting or calculation with the tabular data, like what you saw on this in this previous video, that showing how it's difficult to sort the values of data. Make sense? So without going deeper into this one, and by the way, the most popular graph is called MongoDB. And I don't know if you noticed that the Hadoop system, the graph system, they tend to use the name of animals and the fruit, and they call this zookeeper. Okay, anyway, so the most popular one for the graph-based database management is MongoDB. But we do not need to go into, how to use them, but you just get the sense. The GraphX, the DAC method is basically borrowing the license learned methods from the graph theory to make the search, merging, sorting, calculation of the tabular information much easier. Okay, makes sense? So we do not cover too much. And this one also shows the graph theory can also be used to divide data. Remember, for the MapReduce, there's a critical step is the mapping step. Like I received one and I cut them into blocks and save them in the distributed servers. So one potential limitation of that is I didn't consider the internal relationship inside the data. I just treat them as data. I treat them as 0 and 1s. And I only use one rule, which is 120 megabit to cut the data. But what if my data has some stronger relationship, like for example, this particular segment of data and that particular segment of data actually shows the relationship of one transaction, like a seller and a buyer, okay? But because just by chance, I cut between them, so I basically just send them to separate servers. We still have the complete information, but if I want to calculate their transaction number, think about that, guys. Actually, the mappers or the smaller workers that are running the piecemeal information, the piecemeal operation, would lose the chance to calculate that transaction. Make sense? So basically, we cut in the middle of that transaction and send one to a server in Japan and another server in China. So actually, the only way to calculate, to count that transaction would be somewhere in the reducer. It's kind of like the last step. So it doesn't consider the internal logic of that. So to fix that GraphX, this is also, the graph theory-based method, it covers that. So this is actually how we cut the edge and how we cut the vertex while still maintaining the original information to the maximum. And then we spread them, we distribute them into the parallel computers for basic processing and algorithm again. Actually, when I was doing my PhD, I think that was in 2011, I received an interview from Amazon, and they were hiring a software developer. I think at that time they gave it different names, called data engineer or something. They actually asked me this question. So they basically, during the presentation, it's an online presentation, they showed me a figure of graph and asked me to apply some methods to cut the edge while still preserving the original relationship information. Of course, I didn't get through, otherwise I will be working in Amazon right now. So I asked them why they interviewed me, because I was doing a PhD in civil engineering and they were looking for software engineering and data engineering. But they told me they actually were hiring a lot of people from non-computer science discipline, because to their, I remember it's not called data engineering, it's called a data scientist, okay? So they say for data scientists, programming is not the #1 priority, but logic is their #1 priority. So the data scientist wouldn't be doing the programming or writing the lines of codes. The data scientist is actually proposing new logic, how to better process the code. They also asked me some interesting question, like, I remember that, so Amazon was talking about this kind of unmanned final delivery method, like some boxes in the neighborhood. And they say they have this logic chain. The most expensive one is the last mile problem. Like it's actually very easy for Amazon to deliver their products to some delivery center and local dispatch center, but it basically costs them more than 50% of their cost to deliver their final products to your door. So they basically were having that question, say, hey, Eric, this is my next question. So let's give you this map and just tell me your logic of deciding how many boxes for each community. You guys got a point? So they just ask you questions such as what factors you should consider. Okay, so I just started to think, I definitely consider how many people live in this community, the social economic status of the people, like how much you spend, the numbers of that. What else? Oh, maybe like traffic, like how long it takes to go there. What else? So basically just ask all the questions, this open question. Make sense? It's actually a really good math exercise. All right, so finally we have this particular method, the streaming. So instead of playing, I think I do have the, okay, so let me just play this one quickly. I saw I had the link, but no. This is actually the in and out happen at the same time, okay?
Hi, I'm Tim Berglund. Operating Kafka can be a challenge, but it doesn't have to be. Confluent Control Center is here to make life easier. We've got a series of tutorials that show you how to solve real-world problems with Control Center. But first, we need an environment to control. This video is all about how to get that set up. We're going to take Kafka and Control Center, and we're going to run those in Docker, as well as a simulated application to monitor. That'll be running in Docker as well. For your convenience, the example environment is all on GitHub at confluentinc/cp-demo. That's the repo that we're going to clone and get all the materials from to do the steps in this video. Our example use case is a streaming pipeline based on edits to real Wikipedia pages. Now, helpfully, the Wikimedia Foundation publishes all of the real-time edits to all Wikipedia pages to, as it turns out, IRC channels. Maybe you didn't see that coming, but that's what they do. So using Kafka Connect, we can ingest those changes into a topic in a Kafka cluster. Once the data is there, we can analyze it in various fun ways using KSQL, then write the analyzed data back to Kafka topics to inspect, or use Kafka Connect to dump that out somewhere else. That's our whole pipeline. And in our case, we'll be using Connect to load it into Elasticsearch, from which point we can visualize it in Kibana. All in all, the perfect crime. But first, let me give you an idea of the system we're playing with. Remember, all this stuff is in GitHub if you want to try this at home, and hopefully you do. This video is all about how to install and run the demo, and the other Control Center videos in the series rely on this one, so you'll benefit a lot from going through these steps. Now, you'll need a few tools. We're going to be using Google Chrome, and that's important. We need to be using Chrome and not some other browser. We'll be using Git, Docker, and Docker Compose. Now, you probably at least have Git and Chrome installed, and Docker Compose are not hard to come by with a quick Google search if you haven't used those tools yet. So from there, the first thing we're going to do is clone the GitHub repo containing all our demo materials. This is the confluentinc/cp-demo repo. Note that I'm typing -- recursive in the clone here. This is because the repo uses a couple of Git submodules, and that flag will automatically clone these as well as the top-level repo. If you've used submodules before, you know it's better to do this now. Just do it and nobody gets hurt. What are those submodules, you ask? Well, one of them is a custom Kafka Connect connector to ingest from IRC. The other is a custom single message transform, that's another Kafka Connect thing, that massages the IRC data a little bit as Connect ingests it. We won't go into the implementation details of those very much, but we will build them. So let's cd into the directory we've just cloned. The submodules are both Java programs, so we're going to run a Maven build, which ends up putting the resulting jar files in a directory called Connect Plugins. Here you can see the output of the build, which are all the jars we'll need to tell Connect about later on. All right, next let's get Docker set up. We need a bunch of services running at the same time to get Control Center and Kafka and our demo and all these things running, and each will run in its own Docker container. Docker Compose just makes it easy to bring those containers all up together in an automated way. When I type Docker Compose in this directory, it automatically looks for that dockercompose.yaml file and does what it has to do with the instructions in there. So you can see those containers.
You guys see the Zookeeper, right? Remember what that is? It's actually the streaming service provided by Hadoop system.
Coming up, and I'll do a Docker Compose PS to show you what's running. And like I said, there are a lot of things. There's a Zookeeper, there's a couple of Kafka brokers, there's Elasticsearch, Kibana, Kafka Connect, and the Confluent KSQL engine and schema registry processes are running as well. If you rerun PS later on, you'll want to see that everything Kafka client, if you rerun PS later on, you might see Kafka client has terminated, but all the other things will stay up, or at least should stay up. Now I can peek into the logs of the control center container just to get a warm fuzzy that it's working properly. You see the HTTP messages that are being logged in here. When you see those, you know, okay, control center's up, everything's fine. The demo we're working towards here is going to use Confluent KSQL. Now there's a lot of machinery there, and I don't want to drag you through all the details. This is, after all, supposed to be about control center, so I'm just going to run a setup script that gets things ready. This script is configuring Kafka Connect, it's customizing the cluster name, it's adding alerts and triggers and actions in Control Center, it's creating the Kibana dashboard and the Elasticsearch mappings, all that stuff. It's doing a bunch of drudgery that would normally be a part of the development and operational infrastructure of a real enterprise, but in the case of this demo, you don't want to watch me do it by hand, just so that we can see how Control Center works. So this script is doing all that setup. When it's finished, we can go to Control Center and look at our cluster. Now here is the Control Center landing page, and you can see just by looking around, it looks like we have 2 brokers, which is consistent with what you saw in the Docker Compose PS, if you were paying attention to that earlier. I'm going to change the period here to 30 minutes just so we can see more data on the dashboard. So, sanity check step 1 complete. Our demo is up and running. Now let's look real quick at our Kibana dashboard, and we see data. This is actual live data, in fact, that's just been pulled from Wikipedia since I ran the script. The streaming data pipeline is starting at the Wikipedia IRC channel. Kafka Connect is bringing it into a Kafka topic. KSQL is enriching it in various ways, which we'll look at in other episodes, and it's ending up in this dashboard here. This is, in effect, our application, and it's running properly. Mission accomplished. The next steps will be to go back to the playbook on GitHub and start looking at what's there. You'll get a tour of the Confluent Control Center proper, then a walkthrough of how to resolve various broken things, various pathological scenarios that can happen in a real-world Kafka cluster. Consumer rebalancing, slow consumption, underconsumption, failed brokers, and more. So join us for those episodes as we work through all of those great scenarios using.
All right, so that was a quick introduction to this one of the most famous big data streaming tool, the Kafka. So you get a sense. You know, I'm not intended to let you learn how to use the tools, but at least you know what is the user interface, the workflow of that. So in general, this is also part of the parallel computing. So usually for a long time, people actually use cloud computing and parallel computing interchangeably. Now they have different meaning, but the logic is still the same. All right, so that concludes our talk on big data. If you do you have any comments, questions? All right. If no, let's move to sensors. Okay, so remember this class is organized by the 3 main phases of data, right? So one is the collection of that, the one is the analysis of that, and also the final one is how to visualize the result. So this result communication of that, right? So sensing is actually the way to collect data in this engineering world. Of course, in other domains such as the social science, you know, the data collection could rely on like surveys or interviews, but we are talking this data collection process more in an automated way or engineering way, which is sensors. Okay, so talking about the sensors, you know, it's growing worldwide, mainly because of the Industry 4.0 and the fast development of the Internet of Things. So this is just give you a quick example of different kind of sensors and the units shipment by the product product tab in millions. So let's say occupancy sensors grow really fast. You know, it's around like 15 to 20 million units sent. We have the carbon dioxide sensors, thermostats, and photo sensors. You know, that shows a faster growth, steady growth of sensor shipment worldwide. And this is some statistics. So in terms of the sensor market, the annual growth rate is around 48%. So every year it increases by 48%. And just in the past 7 years, from 2013 to 2020, we observed annual shipment from 1.8 million sensors to 28 million sensors. And the market value actually increased dramatically from around $300 million to almost $4 billion in a 7-year period. So in the US only, we are talking about a $1.7 billion market for different kind of sensors. And by the way, guys, the sensors I here refer to more building related sensors, so such as the carbon dioxide, thermostat, not those kind of medical use sensors. Okay, and in European Union, so they actually published, they actually announced a directive that's 2002/91 EC. They basically required a minimum energy performance on their buildings. And in order to achieve that, a significant requirement of that is actually to have the sensor network in their new buildings. And the US relevant regulation related to the use of sensors in buildings is ASHRAE 90.1. It requires the standards for what we call smart buildings that can automatically track the air quality, indoor air quality, occupancy, and also potential hazardous materials with sensors. And California actually is one of the most aggressive states in terms of pushing the use of sensors for smart buildings. And they have this Title 24 announced in 2014 that give very strict requirements on the new build projects. Usually, I have to say, these regulations only regulate public projects. It's very difficult for the private sectors to regulate their behaviors, since this is free market. But I have to say, this is how technology evolves. Usually, the public owners, the agencies will start regulation, and the private sector just follow up. So sensor application for us, like I mentioned, sensors can mean a lot and it can be used in different areas. For us, the most relevant two applications include the building sensors and the structure sensors. Okay, so the building sensors, can be used to improve the occupancy experience, and also can be used to improve the operation and maintenance. Imagine you have the temperature sensors to tell the facility manager if something's wrong, the pressure sensors to tell if the water pressure is right to support the system. And here I give you some example, like light sensor, fire sensors, circulation sensors, and also electricity sensors to serve different functions. We will talk about some examples. And structure sensors, imagine you want to check the deformation of a bridge, or you want to check the vibration of a big bridge, or you want to check let's say, the pressure of some pipeline, the air pressure, water pressure of the pipeline, the dams, of course, the strain of the concrete. So there's a big research area called Structural Health Monitoring, SHM. Actually, we do have a professor in our department, Dr. Jennifer Bridge, and she's doing a lot of sensor study to monitor the structure, usually concrete and steel. Okay, and some of the sensors are embedded as well. So I know there have been some research that they embedded some chips inside the concrete. And the chips serve as the reinforcement as well as this passive sensor that if you use a reader, the reader will send energy to chips, and the chips will read the strain, the internal strain, like tension or compression of the concrete, and send it back to the reader. So it's actually very convenient. That's embedded sensors. But most of the time we use the multi sensors such as vibrometers, accelerometers, attach them to the structure. We also talk about the imagery-based sensors today, like we can take pictures, and we use the high resolution pictures or slow motion camera to check the vibration, to check the rigidity of a structure. So that's all vivid, variable research topics today. All right. So talking about the popular sensors used for building, we have this carbon dioxide sensors, the proximity or motion sensors to check the occupant behavior, temperature and humidity sensors. This is surface airstream temperature sensors, light intensity sensors. This is good for controlling the artificial light, air pressure sensors, and relative humidity sensors. That's more for adjusting the indoor environment. We can check the AC system, monitor AC system. The infrared I-beam sensors, this is also for checking the occupancy. Particle sensors, so if we want to see some hazardous particles in the building, such as the PM 2.5, so that's particle sensors. And also the sensing, a lot of sensing systems also have this generic data logger. So this is more kind of like the intermediate data logging system to store the data temporarily and also to transfer data, and on-off state logger. And this is more for checking the status of sensors. So this is a popular building sensors. What are sensors? Actually, we do have a official definition for sensors according to American National Standards Institute. So a sensor is a device which provides a usable output in response to a specified measure. Sensor is actually, you can imagine this is a transfer. So we need to read some signals. Most of them are physical signals. And then we transfer that into some other signals that has a meaning. Okay, so this is called a sensor. So with that side, it relies on specified measure. With that side, sensors can be categorized based on their functions, but also can be categorized based on what signals they are reading, what physical signals they are reading. Okay, so it's a transducer, a transformer or transducer. So basically that transfer the physical signal into something useful. So this is actually the detectable physical signals in our world. That's also the stimuli for our sensors, right? So for example, acoustic, the sound, that's actually used by a lot of sensors. Sound means the waves, right? So the sensors, what the sensors, here you can imagine here is basically the physical phenomena, and these are the features from that, right? So for sound, we could check the magnitude, we could check the wave, we could check the spectrum. Can anyone still remember what is spectrum? What is spectral analysis? Do you guys still remember? We talk about that. The distribution of frequency, right? So one sound is actually a combination of different frequency, right? And so basically, this spectral analysis can tell which frequencies is the most significant. Biological chemical sensors, such as some chemicals and gas and liquid, the fluid concentrations. Electric sensors, we can check the charge, the voltage, the current, and also electric field, conductivity, and the permittivity. So imagine here are all the features we extract from the raw electricity, and then we can use them for different purposes. If we are smart, we can definitely, I will show you some examples, some representative sensors in civil engineering, and this is actually a very smart use of the features from the physical signals. Magnitude, of course, that's also used by a lot of sensors. The magnetic field, such as the amplitude, the phase, the polarization, the flux, and permeability of the magnetic field. Optical, which is light, such as the reflectivity, the absorption, the refraction index from the light. Thermal, like temperature, flux, the heat, and thermal conductivity, that's all the features we can make use of. Mechanical, such as the velocity, acceleration, the force, the torque, the strain, and the stress. Okay, so this is very abstract. It shows that the popular physical signals and corresponding features that the sensors are using. But now let's talk about some examples. Okay, before that, let's also talk about why we need the sensors. So sensors actually today are omnipresent. They're actually embedded everywhere, like the phone. It has a lot of sensors. We'll talk about in a moment. By the way, you see this flashing? That's actually a sensor. That's infrared, right? It's actually the phone is trying to read the face. It also has the accelerometer, gyro sensors, and distance sensors. light sensors, so you can adjust it, adjust the light. What else? Sound sensors, right? So you can basically check the noise. So many sensors built in this small device. Without all the sensors, this is boring. It's only used to make phone calls and text message. Cars, you know, you can read your tire pressure, you can read the speed, right? Airplanes, phones, radios, chemical plants, industrial plants, and countless a lot of applications. So sensors are everywhere. So without sensors, we can safely say there wouldn't be automation. So the prerequisite for automation is actually the use of sensors and connected sensors. That's the sensing network. It's also the foundation of the Internet of Things. So if you are the designer of a sensing network, let's say you are designing the sensing network for whale hall, you definitely need to consider three things. You know, one is the environmental factors, such as the, you know, what do you want to sense? And like what is the environment inside this building, right? So like temperature, humidity, is that a potential risk of corrosion? What do you want to cover? What's the size you want to cover? How much energy the sensors will consume? Do they support their own energy or not? So you have to consider this. It's very easy for the whale hall application, but imagine you are designing the sensing network for a nuclear plant. That's all the things you want to consider, right? And of course, you also need to consider the sensors themselves, like their how sensitivity they are, the range of coverage, how stable they are, can you reuse them repetitively, are they error proof? You know, how many times they would give you the erroneous result, and also the response time, like how fast they can respond. And finally, you want to consider the economic factors, right? So how much they cost, and are they available? Can you buy it easily from Amazon, right? And what is the maintenance cost? What is the maintenance cost of that? What is the life range of the sensors? Okay, so let's just talk about some typical sensors. Remember, your second group assignment is designing a sensing network for whale hall to make whale hall smarter and better, right? So it can be serving the students. It can be making the AC much more personalized or better. It can be making the lights more automated. You know, think for yourself. Actually, I really like one solution proposed by a previous student, that they want to develop some kind of sensing network to tell the students if a professor is in the office or not. So that's also a possible use of sensors. So let me go over the motion sensors, acoustic sensors, light sensors, temperature sensors, and finally environment sensors. Hopefully this can give you some base for designing the sensing network for whale hall project. Okay, so accelerometer. I gave you this example, the ADXL 345 sensor. So this is actually a very small sensor. I didn't find the exact same one, but I found this one in my office. I don't know if you guys can see this. It's very small. This is accelerometer. Accelerometer can check the acceleration. So it's not a speed, but it's an acceleration, right? So like how fast I change my speed. And this is the principle of that. Inside this chip, there's a very small mass connected to a very small spring. And this is a piezoelectric material. Piezoelectric material means if the density of that changes, the conductivity will change. So if I hook up something that can measure the voltage going through this piezoelectric material, then I can tell how much the density of this material changes. Make sense? And the density change drives by the mass of this one. And this is just the nominal mass. What I mean is if I accelerate in certain direction, then the nominal mass will change and change the density of this piezoelectric material and finally the voltage. So I just read the voltage, I can recover the acceleration. Make sense? And now the entire device here is only this size. I don't know if you can see this little yellow dog over there. You guys can see that? Just imagine how small we can make this thing, just this yellow thing. That's the entire device. All right. So we have so many methods, but this is the most popular one using the piezoelectric. So potential applications can be, let's say, you know, I want to check the vibration of a bridge. Okay, the vibration of the bridge. Remember, I showed you guys the TEDx talk that we use the camera to check the vibration, we recover the rigidity of the bridge, right? And also something like the infrastructure-free localization. So I want to show you a very interesting example. I think it's this one. But how we can use accelerometer to check the track the location, to track the trajectory. So let me ask you this quick question. So we don't have GPS here. But why, when this person moves this device, it can actually plot the trajectory of that? Anybody? Acceleration means what? Means the change of speed, right? And also change of direction. So if I define my original point at 0, 0, 0, if I know the acceleration at every frame, let's say I track it as 100 hertz, which means 100 data points per second, then I can recover for that 100th second, like how exactly this thing moved, and then I could definitely recover the trajectory. Make sense? All right. Not exactly. What are we still missing? Can anybody tell me? Accelerometer tracks the change of speed. It's actually just the change of speed. It's not tracking. So this accelerometer is not tracking the change of direction. So what am I missing? We are missing also the pulse of this device, right? So that's why in order to have this infrastructure-free localization, we also need this thing called the gyro sensor. The gyro sensor actually checks the pulse of that. It uses the phenomenon, physical phenomenon called a Coriolis force. You guys know what is Coriolis force? It means that when something is rotating, and then you will have some nominal force perpendicular to the movement direction. So basically that supposedly to go like a linear line, it will basically move, bend a little bit. That's why we have hurricanes, because Earth is rotating. So when the hot air is moving from south to north and cold air is moving from north to south, because Earth is rotating, they basically will bend. And then because of that, we have hurricane. Make sense? So let me just show you a quick video that of what that means. So let's say it's not moving, and if I throw a ball to that person, the ball will go a straight line, all right? And now let's rotate the thing. I still throw a straight line ball, but see what happened. The ball goes to a curved line. And this force is not a force, it's actually because we have this kind of angular acceleration, but anyway, we treat it as a force. The force is bending that, right? So now this is actually the principle for making this gyro sensor. The gyro sensor actually has this 3 components. We have the stator basically fixed there. We have this sensing arm, and we have the 2 drive arm. The drive arm is always vibrating. Okay, vibrating, you can imagine it's kind of like throwing the ball from here to here. That's how it just keeps throwing the ball. That's called vibration, right? So they have vibration like this one, all right? And then when this thing rotate, which means I change the pulse of that, like my phone, I just rotate a little bit, I change the pulse of that. Then what happened? Kind of like in this video, the ball goes a bend curve. Here, the vibration wouldn't go a straight line. Make sense? So the vibration pattern will change a little bit, like vertically, okay? It's kind of like the curve or the trajectory of the ball changes. So same thing here, the vibration changes. And then this sensing motion, this sensing arm will notice the distance change from it to this arm and to that arm. And just by reading that, we can recover the pulse change. And we can, once again, we can make it really, really small. Yeah, this is the one I have. Actually, remember the yellow dot over there? It actually has a accelerometer as well as a gyro sensor built in. Just that small. It's amazing. It's actually a piece of a engineering miracle. And it's very cheap. This one is only $6. You can buy it from Amazon. I think there's another video showing the principles of that. It's here.
Acceleration value. Next is the gyroscope, which measures angular rate using the Coriolis effect when a mass is moving in a particular direction with a particular velocity, and when an external angular rate will be applied, as shown with the green arrow, a force will occur, as shown with the blue arrow, which will cause perpendicular displacement of the mass. So, similar to the accelerometer, this displacement will cause change in capacitance, which will be measured, processed, and it will correspond to a particular angular rate. The microstructure of the gyroscope looks something like this: a mass that is constantly moving.
This uses different design, but it follows the same principle.
Or oscillating, and when an external angular rate will be applied, a flexible part of the mass would move and make the perpendicular.
See, that's basically this is the sensing arm, you can imagine, and this is actually the vibration arm. And because you rotate that, so you have an angular rate, and then the distance between a particular vibration arm to the sensing arm will be different. And just by reading that, I can notice, I can recover, how you rotate that. And because of this entire amazing process, we can have such a thing called infrastructure-free localization. That's actually a battery connected to Arduino board. This is gyro sensor plus accelerometer, all right? This is what the steps of this person. Recover the steps of this person. Imagine the possible use of this thing, guys. I can track how this person moves inside a building. I can track how this person, what's the speed this person is moving. I can check the gait of this person. The gait means the gesture this person is moving. And that is a strong indicator if this person is tired or not. So just by adding this sensor, I can make it a safety device. I can make it a health monitoring device. I can make it a construction worker tracking device. I can do a lot of things with that, right? And also I can connect this one to some kind of a speaker system and with your ID. So if I track you are approaching certain, let's say, shopping mall to a certain store, I can play some customized, personalized commercial to you. See, this basically shows this person was climbing the stairs. All right, quick question, guys. Why don't we use GPS for indoor localization? Anybody?
Maybe some connection issues.
That's correct. To put it simple, we cannot use GPS indoor because GPS relies on the satellite system, and the signal is actually very, very weak. So think about, you need to rely on at least 3 satellites to triangulate your XYZ. Even though in the outdoor for civil use, the accuracy is actually within, I think the latest one is still within 5 meters. So actually, we are not talking about a very accurate. The reason that you can use your phone to navigate while you're driving a car is because we have some AI component inside. If you are close to a road and you are moving at a speed of 70 miles, very likely you're on the road. So the AI will correct the tracking and put you on the road. Makes sense? But just by tracking itself, the accuracy, the precision is only about 5 meters. Inside a building, indoor, it's actually more than 100 meters. It's impossible, it's useless. I want to track the location of Eric Du inside this warehouse, but I tell you, it's 100-meter range. It's from that end of the building to the other end of the building. So it's impossible to use indoor localization. That's why people have been trying so hard to develop technologies for indoor localization. The most popular one is using infrared light. So imagine you have two infrared lighthouses shooting infrared lights to you. You have a receiver, so it can triangulate XYZ. It's actually very similar to the GPS system. It's just the difference is we have some smaller satellite built inside the building to triangulate XYZ, right? We also have some applications using sound. So it's very similar, right? We just need some source to shoot at the ultrasound and to triangulate, based on the reflection to triangulate their location. And some smart people are also talking about use the LED light. So they basically put the LED light as a grids on the ceiling. And then if you walk underneath a LED, you would reflect some light. So they put the sensors next to the LED light, they will see some stronger reflection from something. And by checking the grid of LED lights, they can see how you move inside the building. Makes sense, very smart. But the most popular, the most hot topic today is infrastructure-free indoor localization, which means if I send a firefighter into a building, and I don't have the privilege all the time to install the infrared light, ultrasound, or whatever thing inside the building, can I still track the XYZ, right? And the current solution is actually two directions of research. One is based on the cell phone signal. So our phone is actually talking to the towers at a very high frequency. And what if I can read, the very slight difference of my phone talking to two towers, maybe I can triangulate location. And the other one is actually using the accelerometer and the gyro sensor, okay? Actually, there's an app in my phone. If we were seeing each other, I would definitely, sorry, my throat is soaring a lot. So if we're seeing each other, I would definitely show you that. It's actually very interesting. What's that? Augmented. Here it is. Okay, so this is called AR Magic, and you can definitely see some other AR apps. This one is using my accelerometers and gyro sensor, and so basically I just use my phone and move it in the space and plot something. It's a 3D object I'm plotting. I leave the home, I come back, the 3D thing is still there. So think about what happens. It's not because I created something in the room and it stays there. No, it's my phone is actually tracking the XYZ of this phone all the time and trying to render that virtual fake object to the same location. Okay, so that's a very interesting why it's loading very slow, but yeah. And there's a potential problem with this infrastructure indoor localization. It's called drifting. So what I mean, I'm trying to show you. Let's say you guys can see my pen, right? Okay. Let's say I start from here. That's my original point, and I just basically move this way, and I move this way, and my intent is to go back. Okay. So if my tracking is accurate, I will definitely return to the original point. But this kind of accelerometer and gyro sensor tracking is not always perfect. So I will basically, the track the position probably goes like this way, right? And then it probably goes this way. And then it probably goes this way. and probably goes this way. And the arrow will what? Will accumulate. The arrow will accumulate like this. This is called a drifting problem. Make sense? So after a while, your tracking would be totally off because you basically, the arrow builds up and start to drift. This is the most popular research topic in indoor localization today. They are using what? Just give me a quick answer. They are using what to correct the drifting?
Spectrum analysis.
Was that? No, not spectral analysis, machine learning. So they try to learn from the arrow and try to correct the arrow using machine learning. National Institute of Standards and Technology NIST actually awarded $3.5 million, to a CMU team just to apply this machine learning to correct this drifting problem. Very interesting. And talking about the indoor localization problem, infrastructure-free indoor localization problem, NIST also has this computation. Let me search indoor localization. Here it is. Like this contest. Winners. They basically send you, see, if you basically just compete for that and they award you $20,000 cash. They send you to some basement and they blocked all the cell phone signal and there's no light. They only give you a phone. You can play with the phone whatever way you want. And it all depends on how well you use the algorithm, machine learning to correct the errors. But the sensors pretty much is just the accelerometer and the gyro sensor. And the winner is this team from Texas A&M, Corpus Christi. So I know these guys. I met these guys actually in San Diego in 2018. So it's amazing that they won this. They basically did this in this 30,000 space. But guess what is their precision? It didn't mention here in this article. 15 meters. So by reducing the tracking precision level from 100 meters to 50 meters, that would represent the cutting edge technology, and you got $20,000 cash. So that shows how difficult it is, all right? And also a very interesting use of a gyro sensor and the accelerometer. Another sensor that is similar is called a Vibrometer. But unlike accelerometer, this Vibrometer can only tell you vibration or not. It doesn't tell you the acceleration. You guys understand what I mean? So you guys understand what I mean? So this is more focused on the vibration magnitude, but it's not. So it basically only works in one direction. It doesn't work in the 3D direction. So this is more useful when you check the vibration of a structure where the structure always vibrates in one direction, or the damage of one direction is more severe. So in that way, you want to use vibrometer. I also have one here. You see this guy? Okay, and similarly, it's also using this piezoelectric sensor. And in here, you see this little chip is very thin. That's actually the one. So let's say I attach this one to my hand or to my desk, like this. Okay, and if I just basically just vibrate or touch it, click it, it will change the, how to say that? That kind of vibration will change the thickness of this thing very slightly. And this one attached to it can read the change to the voltage and send those to this chip. The chip is actually very, very simple. There's no chip, it's just an amplifier, and then send the signal back. And we can check vibration. That's very, very easy. So the potential application is like check vibration blast, if I want to see if something blasts. If I want to, let's say for the mining industry, this is also a good one, right? For tunnel, right? For earthwork, the impact, shock waves, airbags. So for example, you're driving a car and they basically use, nowadays actually use accelerometer a lot. So it's actually faster, but before this is a vibrometer. So if the vibration is stronger than certain number, it means you hit something heavily, then it release the airbag. Make sense? Heart monitors. Heart monitor is this too, you know, like heart monitor use different approach. Like this one, you can, if you attach it to your heart, it basically check the vibration, but we can also use the electricity of the heart. So when a heart beats, it generates electricity field, electrical field, we can read that. Or we can use infrared. I don't know if, so like this is Apple Watch. And if I check the heartbeat, so you see this, it's flashing. Goodness. Let me vary it. So basically, let me just describe that. You see, actually, there's some infrared light, and when it tracks your heartbeat, it shoots out the infrared light. And guess why it can track your heartbeat? Because when your heart is beating on your skin, it basically vibrates a little bit. And just by checking that slightly change to the reflection of the infrared light, this one can check the heartbeat. So very small change in the physical signal. And this is a vibrometer. So vibrometer is different than accelerometer. You guys understand the difference now? This is a more simplified version of accelerometer. Of course, we have other device, other methods. For example, the one that use the Doppler effects called the laser Doppler vibrometer called LDV. What is Doppler effects? Anybody? Anybody? Come on. So when something moves away from us, yes. So let's say when a car is approaching you, you always hear the sound becomes sharper, because basically remember the spectral analysis. Now you can use that knowledge. So basically this shows different frequency, but when the object is approaching you, it will move to the high frequency end. So basically the energy distribution will move to the high frequency end. So in human ear, you hear the sound becomes sharper. And when the thing moves away from you, the frequency will move to the lower frequency range, and you see it become flatter. And we also apply this to, it applies to all the wave, including light. So this is how we can tell the universe is actually expanding and it's accelerating. Why? We just check the light of the stars far away from us, and we know based on the chemical components, we know how the light should look like. But we see most of the stars that showing reddish light. What does that mean? So this is purple, this is red. The reddish light means what? Means it's moving to what? The lower range of the frequency, which means they are away from us. They are not approaching us, but they are leaving us. And why we know the universe is accelerating, the expansion is accelerating, because we check something that is further than those stars, we see is moving severe to the right. So we know the universe is not only expanding, but also accelerating. That's why the universe science is the cosmics is so interesting, because there must be some, it's not like an explosion. Explosion means the biggest acceleration only happens at that explosion moment. And then even though expanding, but it will slow down, right? Imagine a firework explode, but the acceleration will become negative because the speed is the highest when it explodes. But when it starts to explode, it will slow down, right? But our universe is so interesting. It's exploding, it's expanding, and it's becoming faster and faster. And the speed is actually, much, much, much faster than the speed of light. Okay, so there must be something pushing the universe right now, continuously pushing the universe. So that's actually the use of Doppler effects. Okay, so now let's come back to civil engineering. the laser Doppler vibrometer is often used to check the structure, like for example, a bridge, a building. And the benefits of using this one is what? This is contactless. This is a contact-free method. So if there's no way for me to go, let's say after earthquake or something that is inaccessible, I can basically put this laser Doppler vibrometer and shoot to the object. I can still tell the vibration. Make sense? So it's basically using that every time when the vibration happens, there must be a moment that the structure is approaching us and then moving away from us. That's vibration, right? So by doing that, I can check the Doppler effects and translate that back to the vibration. But it's very expensive, about $10,000. Make sense, guys? Motion sensors, that's also a very popular sensor. So we use, for example, infrared, we use microwave, but the thing is, the limitation is it creates this kind of a dome. You know, we have a central source shooting out either the infrared light or the microwave. So the closer you are to it, the coverage will be smaller. But if the further away, the signal will become weaker. So that's actually the limitation of that. But this is so common. I don't think we have one here, but this is so common for residential and commercial use today. For example, the lights, you know, Vale Hall is actually a building from last century. Actually, a lot of modern buildings have this motion sensors or occupancy sensors to control the switch on off of the lights, right? That's actually very useful use. And this one shows the typical parameter of that. Usually it covers about, you know, the depth of it can cover is around about 9 feet. That's actually the ceiling height of most of the building. And the size is about a 40 feet or 13 meter range. So it's actually the size of a room to track the motion. Motion sensor, we have so many solutions. We have the passive infrared. The passive infrared is different than the active infrared. So this one doesn't require a lighthouse to send out the infrared and check the reflection, because we as human beings, we have temperature, which means we are emitting infrared lights all the time, right? So if we have the infrared light reader, we can see our bodies emitting the infrared light. So by checking that, we can check the occupancy or the motion of a person. But the benefits is no energy needed for the sensing system, but so we don't have the lighthouse, right? But the disadvantage of that is, what if the environment is too hot? And in that way, we could totally distort the signal, right? Microwave, we basically just send out a continuous wave of microwave, and we check the reflection. Question, guys, why a microwave? Why macro, not a bigger wave? Anybody? This is physics 101, guys.
Maybe to travel faster.
It's faster, it can easily penetrate the buildings, but more importantly, when the frequency of a wave is higher, which means it's vibrating faster, it behaves more like a particle. So it's easier to bounce back. The reflectivity is better, makes sense? But when the wave is, you know, if the frequency is smaller, which means the wave is bigger, it tends to penetrate you, okay? So it tends to just go through your body, and most of energy will be going through, not bouncing back. So that's why we use microwave. Everything makes sense, right? So microwave, ultrasonic, similarly. Why ultrasonic, not just regular sound? Why? Because ultrasonic means the sound is higher frequency or it's vibrating faster. So it behaves more like a ball. So it hits you and it comes back, right? And also we have the imagery solution like the camera. This is based on the machine learning or computer vision. So if I recognize this is a person, and basically even though this is one camera, but I can calibrate that. I know a regular person should look like this much or this many pixels in my image. So when the pixel number increase, I know it's closer to me. When the pixel number decrease, I know it's farther away from me. So even with one camera, I can somehow tell how you move inside the building. Makes sense. That's imagery based. But the disadvantage of that imagery based method is what if it's dark night, and also people do have concerns about privacy, right? But this imagery based localization is also very popular. So let me just see. Imagery based indoor. Maybe camera. This is actually the reverse method. This is a human carried camera. And this camera recognizes the view and trying to match the view with the real environment. So you can basically navigate yourself. This method is called SLAM. And this is usually robots use to navigate themselves. They just totally rely on the image data, trying to match what it sees to the actual building area, and then locate itself in that way. So I need to find a real camera-based localization, not this SLAM-based method. Yeah, like this. Oh, that's also. No, that's also a SLAM-based method. So anyway, this is a good example of SLAM-based method. I know, this is the first-person view of my camera, like I'm carrying a smartphone, and I can match by checking the shape of this one from this 3D to 2D projection. I can somehow know, oh, I'm looking at this set of wall, and because it's changing this way, I'm moving towards this set of wall, so I can locate myself. Make sense? That method called SLAM. SLAM is called simultaneous localization and mapping technology. SLAM. And let me see. Maybe we should add this surveillance. This is. Okay, cannot find it. Yeah, like this one. So this one, you have a fixed camera, and just by checking, see how this person, the size is shrinking, and also the pixel number is shrinking. I know like how fast you are moving away from this camera. That's how we see. You basically locate the person. Now you see that how much effort people are using to realize this indoor localization method, because number one, we need them. Number two, we cannot use GPS. It's so difficult. So we have been talking about the infrared, LED-based, infrastructure-free based on the accelerometer and gyro sensor, and this camera imagery-based method. It's a very extremely hot topic today. All right. So now use your imagination, like for your second team assignment, if you want to check if Dr. Du in his office or not, think about some smart sensors, but also consider what? Not only the sensor characteristics, but also the environment as well as the cost, okay? Definitely want to use some cheap solution. One solution can be just to give you just my 2 cents. If I'm moving my mouse, because very likely 90% of time, if I'm in my office, I'm very likely to just move my mouse or use my computer. So if you can somehow sense that, you know if I'm in my office, right? Advanced motion detection, this is also very interesting. This is called a tomographic motion. It basically uses the established source of information, for example, Wi-Fi. Like our environment is full of Wi-Fi signal. If I'm moving in this building, I'm supposed to change the Wi-Fi, right? And this MIT team actually just use that. Just think about how creative we can be in terms of using sensors.
MIT is working on creating the Kinect sensor of the future, which can see through walls using simple radio waves. The very early proof of concept uses 3 radio antennas, 2 transmitting and 1 receiving, and could place a person on the other side of a wall within 10 centimeters of accuracy. At MIT's Computer Science and Artificial Laboratory, or CSAIL, a person could walk around a room while being tracked, which is represented by the red dot on the screen. The marks on the floor were only to show how accurate the system is. Being able to track users so accurately presents a number of different uses for the technology.
So this is one aspect of it, which is virtual reality and gaming. And the other aspect, which we think is also very important, is localization. So today there's a huge interest in localization. Can you localize a person using radio signals? And there has been a lot of advancements in, say, Wi-Fi based localization, which require you to actually hold a transmitter. What we're doing here is that we're doing localization through a wall without requiring you to hold any transmitter or receiver, simply by using reflections off a human body. And what is very impressive about this is that our accuracy is even higher than state-of-the-art Wi-Fi localization systems.
One of the drawbacks of the system right now is that it can only track one person at a time, and the rest of the area needs to be completely clear of movement. If 2 people are standing in the room like I was with my camera, I needed to remain relatively still so the system wouldn't get confused.
Another aspect we are working on and hoping to get is, now it's mostly tracking if a person is moving. If a person stops, then it will interpolate his location, and so it will know that it is in his same location. What if the device starts even when a person is just standing and breathing? And so we actually now have an initial algorithm that can even tell us, even if a person is just standing and breathing, pinpoint his location.
Adib also said the system allows for 3D tracking and could be useful in telling when someone has fallen in their home. In addition to tracking multiple people at once, the team is also working on making the system a bit more compact.
We can put a lot more work into miniaturizing the hardware.
Anyway, this guy's so nervous. Let me check the second link.
This video shows Wi-Fi, a device that can track human motion behind walls and in closed rooms. Wi-Fi is behind the wall as indicated by the red arrow. The blue window at the bottom shows the output of Wi-Fi. The room is initially empty. This is why the signal is 0. A person enters the room. As he moves away, the device shows a negative signal. When he moves toward the device, it shows a positive signal. When he stops, it outputs only the 0 line, meaning there is no motion. Even when he performs a minor movement like now, Wi-Fi registers it.
Now I got a sense. You know, do you guys know what was my first impression when I saw this research? There's no such a thing called privacy. You know, even though you would think it's safe, but everything can be used to track your behavior. Not just camera. Let me see what's the third link is called.
Y-Track is a new technology that performs 3D motion.
Yeah, this is actually a more in-depth explanation of their method. I just quickly go over it.
But it can also track his body parts.
Yes, you know, they are smart in terms of method, but they're also smart in terms of potential application. Like, if I can track your body motion, I can track if you use your hand, raise your arm, and then I can translate that into some signal to switch on the light. So you might, imagine in this room, you're kind of like a Superman. You're just doing some certain body gesture. You can control the device over there. Very smart, infrastructure free, based on existing infrastructure, right? Applications. That's actually the building, the indoor localization sensor. Their applications. Let me check with this.
The promise of smart and responsive environments relies on the ability.
This is actually, here I'll show you a couple of videos of using, the sensors I have talked about in the Vibrometer, gyrosensor, image-based, and how it could change
events,
the
such
life.
as appliance use and human activities. Currently, to sense these types of actions, one must either upgrade to smart appliances or attach aftermarket sensors to existing objects and work surfaces. These approaches are often expensive, inflexible, and cumbersome to maintain. We present a new, low-cost, and practical approach to sense activities across entire rooms based on long-range laser vibrometry. We were inspired by light-based eavesdropping devices used by the KGB in the 1950s. These setups bounce light off of distant reflective surfaces, such as windows. Vibrations, such as speech, cause minute surface perturbations, which alters the light path. If we place a photosensor in the reflected light, we can see changes in intensity that correspond to the remote vibrational signal. Relying on existing reflective surfaces like windows and mirrors limits the placement of the light source and sensor. Ideally, we want to place the emitter and receiver together in one small sensor package that works at any angle or distance. To achieve this, our system uses small tags made from retroreflective material. These are placed by users onto objects and surfaces they wish to reveal to our system. Only objects that are tagged can be found and sensed. Our system uses a steerable mirror to control the location of sensing. Periodically, our system scans over an environment to find tags. Once tags are found, the system cycles between them to sense the vibrations of their host objects. Using this data, we can create vibrational spectrograms of remote objects. With machine learning, we can tell not only what a device is, but also whether it is active or not. Note that unlike a microphone, our technique senses vibration at one specific point at a time, and thus is robust in noisy environments. In this example, multiple appliances are running, and yet we can sense the vibrations of each device independently. In addition to detecting if devices are running or not, our classifiers can also be trained to recognize different states, offering fine-grained activity information.
Okay, I'm going to stop here, but just think about how smart we can use different physical signals, right? So just use your imagination. I think I have some cool videos. Let me check this one.
Are you trying to balance your 7 different extracurriculars with going to church, going to the gym, hanging out with friends?
Oh, that's me. Okay, I played that already. What's this? Oh, this is amazing.
When sound hits an object, it causes that object to vibrate. The motion of this vibration.
So guys, I need to use the restroom quickly, but watch this video. Okay, it's only 4.5 minutes.
Creates a subtle visual signal that's usually invisible to the naked eye. In our work, we show how using only a video of the object and a suitable processing algorithm, we can extract these minute vibrations and partially recover the sounds that produced them, letting us turn everyday visible objects into visual microphones. In the silent high-speed video shown here on the left, we see the leaves of a potted plant shown on the right. The video was recorded while a nearby loudspeaker played the notes to "Mary Had a Little Lamb." Even when we play the video in slow motion here, the vibrations caused by the music are so subtle that they move the plant's leaves by less than 1/100th of a pixel, making the plant appear still to the naked eye. But by combining and filtering all of the tiny motion happening across the image that you see, we are able to recover this sound. In our next experiment, we recovered live human speech from high-speed video of a bag of chips lying on the ground. But to make things a little more challenging, this time we put the camera outside, behind a soundproof window. This is what a cell phone was able to record from inside, next to the bag of chips.
Mary had a little lamb whose fleece was white as snow, and everywhere that Mary went, that lamb was sure to go.
And this is what we were able to recover from high-speed video, filmed from outside, behind soundproof glass.
Here we have a little lamb whose feet was made of mud. And everywhere that lamb restored to God.
In this next experiment, we recover music from high-speed video of some earbuds plugged into a laptop computer. Then we take our recovered sound and use audio recognition software to automatically identify the song that was being played. Most frequencies of audible sound are much higher than the frame rates of standard video. So all of the results we've looked at so far were recovered from video captured by a high-speed camera, which can record thousands of frames per second. But in this next experiment, we show that by taking advantage of artifacts caused by the rolling shutter in most consumer cameras, we can sometimes actually recover sound at frequencies several times higher than the frame rate of our video, letting us recover audio from video captured on regular consumer cameras. Here we see a 60 frames per second video of a bag of candy captured on a regular consumer DSLR while our Mary Had a Little Lamb music played through a nearby loudspeaker. By using a variation of our technique on the rows of the recorded video, we are able to recover this audio, which includes frequencies more than 5 times higher than the frame rate of our camera.
Isn't that amazing, guys? You know, use image to recover sound, all right? Okay, so let's keep talking about the sensors we have. We have enough time. So this is ultrasonic ranger. You know, this one can basically check out the distance between the sensors and something. So if something's approaching you, you can check it. And I do have one in my hand. One is a speaker, one is a microphone. So basically, one of the speakers is sending out some sound, ultrasound, and then the other one is actually receiving that. But how do I tell, you know, since ultrasound is continuous, right? So how do I tell the one that I'm receiving is from what, when it got transmitted, right? Got to shoot out. So we have to generate some pattern. That's why the ultrasound is not just a flight sound going there and coming here, because there's no label related to the sound, right? So we generate some pattern, and based on the pattern, it's called the pulse. And then we can check the echo time pulse. So we basically use that as the label for my sound. I know, oh, the one that I'm receiving is actually from 2 seconds ago. And now if I know the speed of sound in a regular temperature, I can basically recover the range. So how this one can be used, what is the potential use of this one? Let me just show you a video later, but this is actually a sound sensor. I don't know if I have one here. Anyway, the sound sensor is actually very simple. It checks the how loud the sound is. The thing is, this is actually the internal structure. It's very small. I think I have one over there. It has the dust cover. It has the case, but it has this amplifier. So basically, it amplifies the sound. It's microphone. Application. This is a good application for ranger. For ultrasound-based ranger or whatever ranger. See? That's how useful it is. Right? So next time you can use this one to your boss if you're playing things. Ranger can also be used, can also be realized with this infrared ranger, or this is RI ranger. It's based on infrared light. So let me see if I, yes, here. This is infrared light. This is rebuilding already. So basically one is shooting the infrared light, the other one is receiving that. So based on the reflection, and we know the speed of light, so we can tell the range as well, right? And this is how small it is, all right? Light resistor oh, sorry, that's not the eye ranger. That's this other one. This is actually a lot of resistor sensor. So basically, this is used photoelectric effects. What that mean? Remember why Einstein received that Nobel Prize? He discovered this photoelectric effect. So when this particular device, the material is receiving photons, it will release electrons. So photons, electrons. So the more photons you're receiving, the more electrons you are sending out. And the more electrons means what? Means lower resistance because electrons can move freely. It's just a simple physical phenomenon. So we use that to check the density of the light. So if the light is lighter, the more electrons will be released and lower resistances. So I basically measure the resistance of my material. I know how strong the light is. Very simple. IR sensor, I talk about that. You know, it's very small. It's over there. Temperature sensor is use something called a Peltier feedback effects. I wouldn't cover the exact physical thing, but the thing is, you know, when temperature changes, the density of the metal will change. Make sense? So when it's hotter, it becomes bigger, and the density will become smaller. When it's colder, it will shrink. The density becomes stronger. And for metal, the density change means the conductivity change. Makes sense? Because metal is basically the electrical field will go through the metal, and the metal is sending the electrons going inside the metal. So the density change will make it either more difficult or more easier. So we have basically this temperature sensor uses two different metal, and check the voltage between the two metal. So when temperature comes, the two metal will change differently because they are different materials. The density will change differently. So we measure the conductivity through the difference between the two metals, and we can tell the temperature change. Okay, so that's the temperature. And I have one here. Okay, this one can change not the temperature, but also humidity. Okay, so humidity and temperature change. All right. By the way, this is Arduino. And I used to have this Arduino in-class project with you guys, but this year we would just do a demo. But you know, this is actually the board Arduino chip, and you see this chip. So basically, you just plug them in, or you use the cables, the cords to connect them, and you connect it to power, and you basically program the thing with Arduino and burn them into it. So it has a chip here to store the program, and then you can realize whatever information you need. It also provides this connection to USB. So if you want to read data in your computer, you can read data, or you can just store them temporarily here. This is Arduino Uno R3. This is Arduino Mega 2560. So the difference is they have different number of connections, different number of analog connections or electrical digital connections. Okay, so that's actually will be used in the project. This is a breadboard. So this one means if you are developing some fairly complex system, you basically can just insert your sensors on here, so you can get a fairly complex sensor network. So this is temperature, magnetic field sensor. This is also once again using some physical phenomenon, like when the magnetic field go through some material, the voltage of the material will change, follows this formula. So I think you have a sense now, right? The sensor is actually a smart use of the natural physical phenomena and translate that into what we need. Carbon dioxide gas sensor, that's also very simple. The carbon dioxide is actually fairly big air particles. And so we just shoot this either laser or infrared lights into this small tunnel, and we calculate how much infrared lights are absorbed by carbon dioxide. So we know how many particles of carbon dioxide inside this tube. And before that, we definitely need to know for certain frequency of infrared light, how much will be absorbed by this carbon dioxide. And so I'm going to stop here, but I want to show you this one. Particle sensors, this is also used infrared light. It also uses some phenomenon called this Beer-Lambert law, which means depending on the density of the air or liquid, the light will be absorbed in different way. So I want to show this one because you see, previously we have to use this kind of a device. Then this is a tube to send the carbon dioxide, this size to do. But nowadays we can make things so small. Actually, I do have one in my office. You see this device? It can tell you RH, the relative humidity, temperature, the hazard particles, PM 2.5, and the carbon dioxide. And you see this this is little gap. Basically, there's some small laser device inside here. It's shooting laser here and calculate how many things going on. So 600. Don't know if it's working. See? And this one can be used to test. Okay, I will stop here. If you give me a warning, since this can be connected to my phone, if you give me a warning showing the carbon dioxide is too much. So actually this can be used as what? Building occupancy device. When I have students meeting in my office, the number can hack to like 1,500. If there's nobody in my room, it's around 400. When I'm working in my room, it's around 600. When I'm writing papers, it's about 800. So basically it means that when I'm writing papers, I'm consuming more oxygen and releasing more carbon dioxide. So yeah, just give you some quick example of the sensors. And now it's time for you to think about your second homework. The only principle, the only request from me is be creative. Now you see all the examples. You just think about, definitely you can think about something that's so cheap, so creative. All right. So that is our first sensor lecture. Any question, comments? All right. If no, see you guys next week. All right. See you. Bye-bye.
Thank you. Thank you, Bob.